So hello, good morning. Welcome once again to the talks and discussion, Cosmology, Lights and Shadows. And just a quick overview. On Monday, Alberto told us about the standard model. He told us about that it's characterized by 6 parameters, 4 of them describing the background, and 2 of them coming from inflation, like initial conditions. And then one of the predictions of this standard model is the microwave cosmic radiation, from which Ricardo told us about yesterday. He told us especially about the observations of this radiation, and he also showed us how these observations with a power spectrum, they can tune finally these 6 parameters characterized in the model. Today, Miguel is going to tell us about the dark side. The dark side is most of the universe, right? We have the dark energy and then the dark matter. And because the topic is so wide, he's going to focus on dark matter, specifically from the detection of dark matter as well. And, well, one more thing. Yesterday, Ricardo was going to tell us about this baryonic missing matter, but we didn't have time. So if you are interested, we could get together again on Friday. We also have booked the room. So, and then more debate, yes? Yes, yes? No? Yeah, okay. I see quite a few yes. So we will do it on Friday. Same time, I guess. Days, yes. Okay, so welcome to Miguel.
Okay, so the dark side, Darth Vader, myself. And okay, so as Irina said, my intention here with this talk is to maybe to discuss some topics that are related to dark matter, but probably you are not aware about as in the same at the same level, let's say, like for example observational evidences like rotation curves of galaxies, etc. I will focus the talk on the detection, the effort that is currently ongoing to detect this kind of dark matter, this dark matter. So just a general overview. I should start with a brief introduction, commenting on observational evidences for dark matter, and also presenting the lambda CDM paradigm. But Alberto already did it on Monday, so yes, I will just skip this. What happens there? Let's try again. In any case, I think it's okay, no? We just want. Can you give me the laser, the point? Okay. Okay. So yes, I will just skip this brief introduction, okay, to save some time, as Alberto already commenting on this last Monday. So I will just start with dark matter searches. What's the state of the art of these dark matter searches in accelerators, and very briefly, direct detection at the lab, also very briefly, and especially as we are at the IAC, we are astrophysicists. I will focus mainly the talk, this block of the talk on gamma rays, the search of this dark matter in gamma rays. And if we have some time, let's see how the talk is evolving. I would like to to give you a brief overview also of the kind of work that we are developing regarding embodied cosmological simulations. How these embodied cosmological simulations can help us in order to understand how the halos, the matter halos, form and evolve in the universe. And finally, I would like just to point out some open questions in the model. No? So yeah, as I told you, I will skip this. Alberto presented very similar slide last Monday. I would like just to point that as you can see, we have observational evidences for the matter at all scales. Okay, we have many observational evidences at galactic scales, which are probably the classical ones. We have also many observational evidences on galaxy cluster scales, like for example the velocity dispersions of individual galaxies or strong lensing, etc. And also on cosmological scales. Ricardo, for example, gave a very nice overview yesterday on CMV, and we have also this large scale structure proof in some sense, although some people cannot be in agreement with this, but in principle, these are the observational evidences for that matter that are more or less discussed in the literature so far. So again, very briefly, this is the standard cosmological model. Alberto already presented this slide. We believe that the universe started in a big bang, like 13.7 giga years ago, and then it was followed by a early stage of accelerated expansion, no? Called inflation. No? We need inflation in order to also put the initial conditions for the rest of the universe. How the rest of the matter will evolve with time depend very importantly on the initial conditions that inflation can give us, no? In some sense. And then we had the CMV, the creation of the CMV, this early epoch known as the Dark Ages, and then just all the structure start to form, grow, merge, and evolve with time until the present time. So this is more or less very schematic. Put it in a very schematic way. This is more or less the energy content of the universe. Most of the energy content is in the form of enigmatic dark energy, like 72% more or less of the total content. Then we have this dark matter, non-baryonic dark matter, which means no ordinary matter, no atoms. Okay, that is more or less 23% of the total content. And then we have the atoms, all the stars, all the visible matter. I mean, ordinary matter you can see it's just less than 5% of the total content. So Alberto presented in detail this table last Monday. 6 parameters, as Irene already also remembered us. 6 of them, and then we have a lot of, we can derive a lot of other parameters, very important parameters, like for example sigma 8 or whatever, but I will not go into the details. In any case, I think that Alberto gave a very nice overview of the model on Monday. So yeah, the main block of the talk, the matter Sánchez, was the current status of this field. Just to remind you that again, ordinary matter represents probably less than 5% of the total content, okay? And the visible matter, mainly stars, no? Maybe 0.5 or so, less than 1%. This disagreement, let's say, between this quantity here and the 5% of ordinary matter, the difference is called the missing variant problem that Ricardo didn't have time to present yesterday. Maybe it would be nice if on Friday we can talk about it, because I think it's a very interesting topic. But we expect like 30%, as I told you in the previous slide, like 30% of the universe to be some kind of matter, okay? No ordinary matter, which is only 5%. So we have to explain still the 25% more or less of of the total content of the universe in the form of matter. No? This is what we call dark matter, a non-baryonic dark matter. But dark matter that is composed no baryons. No? Yeah, I won't talk about the dark energy because it's a very broad field. All this and each of these, indeed, each of these fields is a talk by itself. So it's impossible to talk about all of them. No? So this is probably the picture that we have right now concerning galaxies. For example, this can be our Milky Way galaxy. Okay, the mass in the form of stars is like 10 to 11 solar masses. Talking now about the Milky Way. Okay. But the total mass is estimated to be like 10 to 12 solar masses. It's like 1 order of magnitude more. No? So there is we suppose that there is a huge dark matter halo surrounding the ordinary matter content in the visible matter, no, of the galaxy. In the same way, the radius of the visible matter here is like 30 kilopascal more or less. And the visual radius, something like the radius that characterize, okay, the dark matter halo is like 300 kiloparsecs. Again, like a factor of 10 or so, more or less, for the Milky Way. But this is the general picture for all the galaxies. Depending on the mass of the visible mass of the galaxy, also we will have a more or less dark matter content, but in principle the halo of the galaxy is much larger than the visible matter there. Okay. Yeah, so it's a good time not to question ourselves which kind of particle can compose this dark matter. No, so yeah, we know that. Because of the observational evidence that we were discussing about before, most of the matter in the universe must be in the form of non-baryonic matter, and we don't know which kind of the matter of particle can be, but at least we know the requirements that this dark matter particle has to fulfill. Let's say, so it has to be neutral because otherwise it should have been detected at the lab. It has to be stable or at least long-lived, as we need this dark matter particle to be present since the early universe up to now. Okay, we need this dark matter particle to be cold. I will explain it in a few slides later. Okay, so right now, just believe me, it has to be cold. I will explain the concept later. And of course, it has to reproduce the observed amount of the matter. This 25% roughly of the total content of the universe. No? So there are some very good candidates that arise in the physics beyond the standard model of particle physics, and we call them WIMPs, from weakly interactive massive particles. Okay, yeah, and why beyond the standard model of particle physics? Because if we just take the standard model of particle physics, we end up with no viable dark matter candidate, okay, particle candidate. Indeed, there is just a dark matter particle candidate from the standard model of particle physics, which is the neutrino, okay. But this neutrino cannot account for the total content of the dark matter that we assume to be in the universe, okay. The neutrino has a very it's very slight, has a very tiny mass, and yeah. Although it's a non-baryonic particle, it has not enough mass to compose the total content of the universe, as I told you. So this neutrino is excluded to at least as a explanation for the total content, for the total dark matter. No? So we have to go beyond the standard model of particle physics, where other
What is the constraint on the?
Yeah, this is also more or less well known. No? These constraints are coming mainly from supernovae explosions. So neutrinos have, it seems that they have an important role in supernova explosions. So you can constrain at least the amount of, let's say, the density of neutrinos, no, that you should expect, no. And there are also other evidences coming from the lab, for example, that puts stringent constraints on the neutrino mass and also on the amount of, I mean, the number of neutrinos, no.
And also from the CMB.
And also from the CMB, of course, yes. Yeah, sure.
If you consider neutrinos, how much matter do you still need?
Yeah, it's a good question. It's like, I think it's like 2.5% or so of the total that you need. Nacho.
You should also mention that the neutrino cannot be the candidate not because there are no many or not, but because they are hot particles.
Yeah.
So
I will explain.
So you need something that is cold in the sense that the speed of light, in relation to the speed of light, they are moving. But you will explain that. So that is exactly why neutrino cannot be the candidate.
Yeah. So the neutrino mass is not enough to account for the total content, but there are also other questions like the fact that a neutrino is hot dark matter, meaning that it has a speed which is very similar to the speed of light. This is the meaning of hot, more or less. No? It is a relativistic particle. So there are problems to form the large-scale structure that we see today. No? If you assume hot dark matter. So I will explain it later. Yeah. So neutrino is we have to think about different matter candidates. Okay. So the standard model does not provide any viable candidates. So we have to go beyond the standard model of particle physics, where a huge plethora of dark matter particle candidates arise, no? That fulfill all these requirements. Okay. For example, the axions, which are very interesting, also for not only from particle physics side, but also for astrophysicists and for example, for AGM physics. But this is another topic. Sorry. There are also, of course, these SUSY candidates, which are probably the most famous ones. No? Like, for example, the neutralinos, axinos, which is the supersymmetric version of the axion, gravitinos, and there are also other exotic theories, let's say, even more than supersymmetry. Like, for example, Carusa claim, where you can find also very good matter particle candidates. Okay. Probably the preferred candidate in the literature right now is the neutralino, and the estimated mass, although there are very large uncertainties, several orders of magnitude indeed in the mass of the neutralino, but the preferred mass for different reasons, not only particle physics but also mostly particle physics. Okay, it's like 100 GeV or so, no? From 50 to 300 or so, but this is more or less the range that people is working with. But this is interesting. We know the requirements that these particles should meet, no? But there are no evidences for their mass. We have no clues about their mass. Astrophysics doesn't tell anything about the mass. Indeed, this huge plethora of possible candidates span like 90 orders of magnitude in mass. No? So there are huge differences. You can find whatever you want to find in these dark matter candidates. So very briefly, as the neutralino is our preferred candidate, okay, and most of the work in the literature right now is regarding this neutralino. I will briefly give a brief, just a few words about the supersymmetry. Supersymmetry, as I told you, is an extension of the standard model of particle physics, which propose a natural symmetry between the fermions and the bosons. Okay, so each particle in the standard model has its partner. No? For example, the photon has a photino in supersymmetry. Electron has a s electron, and so on. No? All the particles in the standard model has its partner in the supersymmetry. Okay. So what you're trying to do is to have a symmetry at the end. No? when you put all the particles together, you have a symmetry, something like a symmetry that particle physicists and physics in general, I think we love. This all the symmetries in everywhere. So supersymmetry is just it's a theory that tries to find a symmetry between the fermions and the bosons. Okay. So the important point here is that supersymmetry seems to be a key ingredient also for superstring theories, which are, as you may know, which are right now probably the most preferred in the literature in order to explain, in order to unify, in some sense, all the theories. No? So you need supersymmetry as a key ingredient to do this, in order to do this. So assuming a given property, the air parity, okay, I don't know what is it. The neutralino is the lightest supersymmetric particle, LSP, and the important point here is the neutralino is stable. No? It's a particle which arises in the framework of the supersymmetry, and that is stable. No? So it fulfills all the requirements that we had in the table before. Okay, all these requirements it fulfill with excellent marks indeed. No, indeed this is very very different, very complicated to achieve in many cases. But in this case, the neutralino arises in a natural way as an unstable particle, no? In the framework of supersymmetry. This is the most important thing I think for us. Yeah. I would also like to know that this air parity, okay, which is a property, is another symmetry in some sense that you introduce in the model to simplify all the equations. This air parity is not introduced to solve the dark matter problem. It's introduced for other reasons, okay, in supersymmetry. You are not going to the theory and tune the theory in order to have a dark matter particle candidate, no. So the theory gives you this stability also of the neutralino, and gives you this dark matter particle candidate in a more or less natural way, or at least not connected to astrophysics. So why cold? Why cold? Okay, so the meaning of cold or hot is just that it depends on the speed, the typical velocity of the particles. Okay, so if the particle has a velocity which is near the speed of light, we call this dark matter particles hot. Okay, if it is the contrary, okay, if these dark matter particles have a velocity which is just a tiny portion of the velocity of light, we call them cold. No? Okay, so we put as a requirement for our dark matter particle candidate to be cold. And why? Yeah, this is because we need this dark matter particle to be cold in order to explain the large scale structure that we see today. If the dark matter particle is hot, we have something like this. Most of the possible structure that you will see will be erased because these dark matter particles are running a lot, no? And they have a very very large, very very high velocity, so they don't feel the potentials, no, of the gravitational potentials in the same way that cold dark matter particles. Okay, so at the end you end up with a universe with less structure. Okay, in the case of there is a intermediate case which is warm. Okay, where you find exactly the intermediate case, more or less a good amount of structure, but still it seems that it's not enough in order to recover the large structure that we see today. So for these reasons, we believe that the dark matter particle, wherever this dark matter particle can be, has to be cold in order to explain the large scale structure that we see today, with a lot of structure, substructure, filaments, etc. This can only be achieved with a cold dark matter particle. By the way, this is what we call the bottom-up scenario, because the smaller structures form first, and then by merging, they form the largest structures that we see in the universe. In the 80s, for example, it was the contrary. People believed, cosmologists and astrophysicists believed that the dark matter particle should be hot. This is what they call top-down scenario, I think, something like that, where the largest structures formed before previously, and then they just split, no, in the smaller smaller structures. But this contradict a lot of observational evidences that we have today. No? So we had to go to a scenario where the matter particle is cold. Okay, that's the main point here. Okay, so the matter searches can be divided depending on the approach that you use. The searches can be divided mainly in three kinds, in three types. The direct detection, where you are looking for, or you expect a scattering of these matter particles on target nuclei. Essentially, you expect that there is a tiny cross section between your matter particle and ordinary matter. Okay, but you are looking for these interactions, tiny interactions, but at the end there are some interactions. So you are looking for this interaction at the lab. Okay. What you measure there is essentially the nuclear recoil, where the matter particle interact with ordinary matter. This nucleus suffer some recoil, and you measure this energy, you know, the energy that is deposited in the crystal, for example, due to this process, and you are trying to measure this energy. You know? This is a evidence of these interactions. There are also indirect detection, where you are looking for dark matter annihilation products, like, for example, neutrinos, positrons, gammas, etc. What happens here is that the neutralino is its own antiparticle. According to supersymmetry, the neutralino is its own antiparticle. So when they meet each other, when the neutralino meet another neutralino, they just annihilate, okay, and emit a large amount of subparticles, like, for example, neutrinos or photons, like gammas, positrons, whatever. So we are looking for these dark matter annihilation products. It's an indirect detection in the sense that you are not measuring the dark matter particle itself, but the annihilation products. Okay. And finally, we can talk about the direct production of these dark matter particles in accelerators. So, as you can imagine here, the energy that you need is huge. But for example, with LHC at CERN, we expect to be able to produce some of these dark matter particles dearly at the lab, and see what happens. No? What are the properties? I will focus the talk on this second approach, okay? Because I'm astrophysicist at the end, so I'm interested essentially in gammas. This is my field. No? These gamma ray searches are being carried out right now by imaging atmospheric Cherenkov telescopes, like, for example, MAGIC or HESS or Veritas. I will explain a little bit more about this later. Or in the space by the Fermi satellite, the NASA Fermi satellite, which is currently in operation right now. Very briefly, these are the main characteristics of these instruments. The Fermi satellite has an energy range about from 10 MeV up to 300 GeV or so. The energy resolution of this instrument at 10 GeV or so is better than 10%, and the field of view is huge. It's about 1/6 of the sky at just one pointing. Okay. The angular resolution is quite poor compared to other wavelengths. It's like 0.1 degree at this energy, 10 GeV or so. But still is very good if you compare with previous gamma ray observatories. As for the ground, for example, the MAGIC, this is a typical Cherenkov telescope, like the MAGIC telescope at La Palma. The energy range is completely complementary. You can see here there is a nice overlap, but the Cherenkov telescopes operate at higher, larger energies. The energy threshold is about 100 GeV or so, and they can operate up to several dozens of TeV, depending on the source, of course. The energy resolution is poorer than 20% or so. Field of view is very, very small compared to Fermi, for example. In this case, we have just 4 degrees or so you have to know where to point your telescope. This is very important. And the angular resolution is very similar to that of Fermi at the same energy, more or less. What is very, very nice, at least for me, what is amazing for me is that we are doing astrophysics. I think it's maybe the contrary. We are doing particle physics space. Doing astrophysics, you are doing particle physics, and vice versa. No? So in some sense, yeah, this field has become now very, very active, and it's called like astroparticle physics. No? This is more or less the name that people give to this connection, no? This overlap between particle physics and astrophysics. No? So you are doing astrophysics and you are doing particle physics. For me, at least, it's very nice. It's amazing. No? So let me just say a few words about these two techniques. As I will spend most of the time in the case B, I will give just a few words about the other two, okay? Right now. Sorry. Yeah, so as I told you, you can product your dark matter particles in principle in accelerators where the energies involved in the processes are huge. So this is what people are trying to do, or we will try to do in the near future with LHC. However, for me at least, there is an important caveat that I should mention. I think that this is not a complete set of your dark matter particle candidate, and even less, of course, you cannot test your dark matter theory only at the LHC, for example, at accelerators, because there is a very important point. I stressed it you before also. The fact that you cannot know if this dark matter particle that you are producing at the lab is stable or not. No? You only measure at the LHC. You only measure this dark matter particle indirectly also as a loss of energy, no? in some processes, no? And you assume this loss of energy to be in the form of a dark matter particle. Okay, so you can extract in this way the mass of the dark matter particle and the velocity or whatever. Okay, but in any case, you cannot be sure that this dark matter particle that you just produced at the lab is stable or not. And we need this dark matter particle to be stable in order to explain the dark matter content in the universe. So we need to complement these dark matter searches at the LHC with other techniques, with both with indirect detection, direct detection, but probably the most important point here can come from the direct detection, because in this case you are measuring very directly what happens with your dark matter particle. You are using the flux of dark matter particles that are around us right now, and this is different. At the LHC, you produce the dark matter particles, but in the direct detection, you just measure the interaction of the dark matter particle that is flying around, okay, with your nuclear target nucleus, let's say. So this is for me at least is much stronger evidence, no, of the existence of that matter. In any case, the complementary you have to complement all of the techniques, of course. Yeah. So this direct detection, as I told you, for this direct detection, you are assuming that the galactic halo is completely full of these WIM dark matter particles. In this case, we are already talking about WIMs. Okay. The dark matter density we know at the solar neighborhood is like this value here, 0.3 GeV per cubic centimeter. Okay, the velocity of these dark matter particles at this radius distance from the galactic centers is like 200 kilometers per second. So what you're looking for again is the interaction of these dark matter particles with some target nuclei that you put in your lab. Okay. I put here a naive calculation for a dark matter mass for a dark matter particle with a mass of 100 GeV or so, which is, as I told you, more or less the preferred mass for the dark matter particles right now. 1 of 10, using these numbers here, a flux of like 60,000 dark matter particles per square centimeter per second. Right now, in this room, you expect this flux of the matter particles just passing through your bodies. So, but in any case, even with this number, it seems somewhat huge, more or less, can be huge at least. It's very difficult, it's very complicated because the cross section, the interaction is very weak. You expect a very weak interaction between these matter particles and the ordinary matter. This is and there are also a huge amount of sources for background that you have to reject before doing anything. So it's complicated, no? Yeah. Ten to the 0.3. This one. Yeah. Yeah, because okay, you extract the amount of the matter in the galaxy from other observations, no? For example, from the rotational curve or cinematic, dynamic, etc. And you construct your dark matter density profile for the Milky Way, and it's easy, no? Once you have your dark matter density profile, you go to the radius of the solar system using this dark matter density profile, and you end up with this value for the dark matter density. Yeah.
Dark matter distribution in the galaxy?
Yeah. You mean?
No, it's a question. Are you assuming it? The dark matter is homogeneously distributed up to this 300?
If you remember the picture that I showed you before regarding the visible matter, no, with the halo, okay. It's just a spherical halo, no? The matter density profile has only air. I don't know if you are talking about this. There is no a dark disk in this model, at least. It's just a halo.
And it's also up to the center of the galaxy. There are dark matter, not only in the halo, just inside the middle of the visible.
You mean in the galaxy? Of course, yes. There is dark matter everywhere. There is dark matter everywhere. What happens is that the visible matter, the baryonic matter, is predominant in the inner regions of the galaxy. That's it. But there is dark matter. Still, there is dark matter. The baryonic matter is predominant, but this is another story.
Is the distribution homogeneous?
Homogeneous? What do you mean with homogeneous?
Because the density, same density everywhere.
No, the density. They feel the gravitational potential of the galaxy. So you expect more dark matter particles at the very center of the galaxy. Yeah. You have a dark matter density profile that decreases with radius. No? Okay. So as I told you, what you're trying to measure is the energy of the recoiling nucleus, no? After these interactions. The challenge is, I told you, very small energy, no? For this recoiling here. Very large backgrounds that you have to reject. You have to be very, very careful, very sure in order to reject all these backgrounds, to know very well these backgrounds. This is very challenging indeed. And of course, you expect a very small rate, no, of these interactions because the cross section is tiny, no? Completely tiny. But even with all these challenges, there are a huge battery of instruments working right now on the field. The direct detection field is incredible. It's very active, no? Even compared to what is happening in gamma ray astrophysics, for example. These people has a lot. I think that they have a lot of money, and they are building more and more sophisticated experiments in order to try to detect these matter particles with this technique. So depending on the channel that you are looking for, I won't go into the details because it's impossible. But depending on the channels, you have different instruments, no? The main channels are ionization, scintillation, and looking for phonons also. And you can see each of these names here correspond to a different experiment currently working, currently in operation. So it's surprising. This is the state of the art of these dark matter searches. Here I put the cross section of the interaction, okay, between the dark matter particle and the ordinary matter, the target nuclei that you are using. And here I put the WIMP mass. No? Each of these lines correspond to exclusion lines coming from these experiments, meaning that above these lines, all the dark matter models that let's see, according, for example, to supersymmetry, to a given framework, this is you have a portion of this parameter space that is allowed for this for dark matter particles to exist. No? So what your intention is to check, to reject some parts of this parameter space. Above these lines, all the dark matter models that give you either a WIMP mass and a cross section above these lines are rejected by these experiments. So yeah, this is the Xenon 100 is probably the most powerful right now regarding these exclusion limits. This portion here is a portion which is very the preferred, let's say, the preferred portion of the parameter space according to recent LHC results and other particle physics reasons. Okay. And also, of course, assuming supersymmetry, always supersymmetry. As you can see, we are right now reaching let's say the interesting part of the parameter space. We are right now rejecting some of the possible dark matter models that you have for these dark matter particles. But still, there is too much room. There is a lot of work to do. This is essentially the same plot with a lot of other instruments. Almost every year, these instruments give you new exclusion lines, more stringent constraints to the cross section of the dark matter particle with the target nuclei. And here, the shadow regions correspond to let's say. Here I show you the preferred portion of the parameter space, no? The preferred dark matter models for your dark matter particles. You expect these dark matter particles. You expect the dark matter particles to have masses around 200 or so, as I told you before. From, as I told you, recent LHC results. But here you are dealing with more exotic scenarios. Or you are just, for example, this area here is supersymmetry, but with some kind of simplified supersymmetry with less parameters, no? And you end up with a smaller portion of the parameter space, of the allowed parameter space. But if you have more parameters in your models, in your dark matter models, you end up with larger allowed parameter space that you can check with these experiments. The important point here is that you have a lot of theories, supersymmetry or whatever, or other exotic models that give you cross-section that span over several orders of magnitude. You have a lot of dark matter particles, a lot of dark matter models, each of those with a given cross-section, a given WIMP mass, etc. And we are trying to check right now what is the exact value of this one WIMP mass.
Here we are always talking about quick interaction. So my point is, at this level of a small cross-section, does gravity is important?
No.
No? So which should be at which level the cross-section? How close has to be particles so gravity can be important?
Yeah, I understand your point. I don't know. Honestly, I don't know. Yeah, but I understand it. Yeah. I don't know exactly.
Thanks.
Mm-hmm. Okay, so coming to gamma ray dark matter searches, as I told you, most of the indirect detection right now is based on the detection of these gamma rays, which are products of this dark matter annihilation, this interaction between a neutralino, for example, between a neutralino and another neutralino. Why gammas? There are good reasons. We just skip them, but there are very good reasons to focus on gammas instead of other gamma generation products, like for example positrons. Although there is a lot of work on other gamma generation products, but probably gamma rays as products of these gamma generations are the preferred for the people that works in the field. There are very good reasons to do that. As I told you, again, these gamma researches are carried out by Cherenkov telescopes from the ground and Fermi and the Fermi satellite. These are the leading Cherenkov telescopes at present. Essentially, there are three, although I put here four. Kangaroo 3 is not working anymore. They have a very serious problem of funding. So they are not working since like 1 year ago or so. So there are three major Cherenkov telescopes working right now. One of them is, of course, MAGIC, 2 telescopes, a consortium between Germany, Italy, and Spain, mainly. 17 meters each, the largest of the Cherenkov telescopes. Okay, it's a single dish, 17 meter single dish telescope. It's really amazing. Then we have Veritas, which is mainly from the USA in Arizona, 4 telescopes, 12 meters each. Then we have HES, which is an effort between Germany and France, working from 2002, 4 telescopes, 12 meters each. Each of them has their own advantages, let's say. Each of them are the best in a very particular. For example, MAGIC has the lowest energy threshold, which is very important for the matter searches. For example, HES starts to work above 200, 300 GeV, while MAGIC can give you data from 50 GeV or even more, even less. Sorry, and this is very important if you want to check some of the preferred dark matter models that we were talking about before. In the near future, the Cherenkov telescope array, which is essentially a joint effort between the previous experiments. I prefer not to put a schedule for CTA. Maybe Irene can give us more details later if you are interested. But in any case, it seems that the future of the field is just a joint effort with all the major collaborations in the field. Okay, so what's the gamma ray gamma generation flux that you expect in your Cherenkov telescope, for example, or in the detector? This flux is proportional to essentially to two factors. A first factor which I call here F SUSY, which encloses all the particle physics of the problem, and a second factor which gives you the astrophysical details. Let's say in the first one is given by this expression here, where the important thing essentially is the neutrino mass in the here, and this is the cross section of the interaction between a neutrino and another neutrino. Here you don't have interactions, okay, with ordinary matter. It's neutrino with neutrino. The cross section of this process. Regarding this, the astrophysical part, let's say, the important thing is that the matter particle, the matter flux is proportional to the square of the matter density. Okay, in your line of sight, you are pointing your telescope at a particular position of the sky, and you have to zoom up the annihilations given by the square of the matter density. And this is because, again, the neutrino is its own antiparticle, so it's the density squared. It has to be proportional to this quantity. This is important. This is important, especially to understand what are the best places to look for the matter, of course, this flux. So, as it is proportional to the square of the dark matter density, you have to look. You have to point your telescopes to those places in the universe where you expect the highest dark matter densities. For example, the galactic center, of course, is probably the ideal candidate because it's a flux, so the distance is also really important. The galactic center is the perfect target a priori. Dwarf spheroidal galaxies also represent very good candidates, as we will see later. Maybe near other near galaxies, like for example Andromeda, nearby galaxy clusters, which are very massive, and you expect a lot of dark matter density to be there, etc. So regarding the galactic center, As I told you, a priori is the ideal candidate because it's very near, so the flux should be high. Here I show you the flux annihilation profile that you expect. This is the angle between the position, the direction of your pointing, okay, with the galactic center. So, for example, here you are looking at 3 degrees away from the galactic center, and this is what you expect, the flux that you expect with the angle, no? With the pointing angle. For different dark matter density profiles, no? For example, probably the preferred dark matter density profile that we typically use is the NFW profile, Navarro-French profile, that gives you a flux profile like this. In this case, it's the same profile, but you are assuming a process to be at work, which is the adiabatic contraction. Essentially, that the dark matter feels what baryons do. The baryons dominate in the inner regions, and they modify the potential, no? The gravitational potential. And the dark matter particles feel this deeper gravitational potential in some sense, and they concentrate even more in the inner regions. And this is why you por Dios. And this is why you are ending up with a higher dark matter densities, no? Yeah, so the galactic center was already observed by Hess and Magic. Essentially, they discovered a point-like source, gamma ray point-like source there, but the spectrum of this point-like source is not compatible at all with what you expect from dark matter annihilations. Then they also discovered in the same region an extended emission, galactic gamma ray emission again, but it was rapidly associated with molecular clouds and other non-thermal processes there that were happening there. Nothing to do with dark matter. And also more recently, new Hess data, the people from the Hess collaboration say that, okay, dark matter is not excluded, can be marginal, can be present there, but cannot account for most of the gamma ray emission that you see there, which is, I think, is quite obvious. So these are the Hess observations. They did a very nice job there. This is the pointless source that I was telling about, and here in the bottom plot, what you can see is the subtraction of these pointless sources here. I mean, you are lowering the level, no, of the figure to see this extending emission. But in any case, the spectrum. This is the spectrum of the source, the pointless source. The spectrum doesn't fit with what you expect with from dark matter annihilations. It has to be this shape more or less. The problem with the galactic center is that it's a very crowded region. You expect a lot of sources to be there. You can expect a lot of gamma ray emissions coming from different objects. So it's very complicated to disentangle between a possible gamma ray annihilation that is happening there from other astrophysical processes. No? So you have a lot of contamination for dark matter searches. This kind of emissions are just contamination. No? So maybe we have to go to other places. For example, dwarf spheroidal galaxies, satellites of the Milky Way are very good candidates also, because you expect a lot of dark matter there to be there. No? Indeed, they are the most dark matter dominated systems known in the universe. They present very, very large mass to light ratios of the order, in some cases, of the order 500 or even more. Although it's complicated, but in principle, you expect a very high mass to light ratios. No? Furthermore, some of them are really near, less than 100 kiloparsecs. So this is also a very good point for us. And the important thing here is that you don't expect the same problem as in the galactic center. Most of them should be at least completely free from other astrophysical processes, no, that can emit in gamma rays. Yeah. So essentially, I can summarize the present status of these gamma ray searches in dwarfs, saying that we found no signal, of course. Cherenkov telescopes observed some of them, probably the most promising candidates, with no success. Also, the Fermi satellite, after 2 years of data, observed many of them, and no signal there coming from the matter annihilations. This is a typical plot in this kind of studies. Here I show you again the cross section, but this time, remember, it's the cross section between a neutralino and another neutralino, okay? No ordinary matter. And here the dark matter mass. No? each of these points correspond to possible dark matter models that the supersymmetry gives you. In this case, it's supersymmetry, okay? So, and these are the exclusion lines coming from, in this case, from Fermi, and in this case, from magic, no? This is for Sege 1, for example, which is one an ultra-faint dwarf galaxy. Well, you can see, as I told you before, above this exclusion line, you can exclude, you can reject these dark matter models. So what you can see here is that we are still we are not touching the interested part of the parameter space. Indeed, we seem to be still very far. You need like 3 orders of magnitude in order to start to touch and to reject the dark matter models. No? So it seems that we don't have detection, but even more, we are really far from detection, according to predictions. No? And of course, using the supersymmetry as the framework, no? as your framework. In any case, if you are going to other exotic scenarios, you end up with quite similar predictions. It seems that we are still quite far. Sorry. Okay. Galaxy clusters, as I told you, they can represent also very good candidates. In this case, you expect some other astrophysical processes to be present, of course, but in any case, they can be a priori very good candidates for these dark matter searches. Indeed, as I show you here, these are again flux annihilation profiles. Okay, these are for dwarfs. You can see that dwarfs, you expect a highest flux from dwarfs coming from the inner regions, but these are for clusters and these are for dwarfs, essentially. Okay, but from clusters, you expect that a higher flux than for dwarfs in the outer regions, let's say at larger angles, line of sight angles. So in principle, they can be very good candidates. In summary, again, Cherenkov telescope pointed there, also Fermi, no signal found, and against similar upper limits or even worse. It seems that we are still quite far from detection. You need to boost your gamma ray signal coming from annihilation several orders of magnitude, like 3-4 orders of magnitude in the best cases, in order to see something there. People are suggesting in the literature how to boost, theoretical boost this gamma ray signal. Okay, so essentially what people is telling us is that you can boost all these dark matter models in order to meet these exclusion lines here, no? Or at least to be quite near from these exclusion lines. But in any case, at least from my side, I think they are proposing quite complicated models in order to boost this gamma ray signal, and I think that at least more work is needed in order to clarify the situation. Yeah, I will skip this. This is the valid cluster. This is a very nice proof. It has nothing to do with gamma rays here, but it was just to mention this case. Maybe if you're interested, this is one of the, I think, most beautiful proofs of the existence of the matter in galaxy clusters, at least, or in general. If you want, I can give you more details. Yeah, and this is, I think, this is quite. I don't know if there are questions. This is the second part of the talk, so maybe it's a good point to just cut and see if there are any further questions or whatever from this part, from the first part.
Any question?
So how the future facilities for Cherenkov telescopes will improve the situation in terms of the
exclusion lines, yes, mainly, no?
So yeah. How far we go?
Yeah, the CTA sensitivity, roughly speaking, will be better than the typical Cherenkov telescopes sensitivities right now. 1 order of magnitude better. How this translates in these exclusion lines? Not very much, actually. Not very much. Less than 1 order of magnitude. Yeah. According to these predictions, yes. which are, as I told you, the preferred, in principle, comes from the preferred framework, no? Supersymmetry, even more, M-Sugra, which is like a small portion of supersymmetry, which is very well, I don't know how to say in English, it's very well motivated, okay, M-Sugra. And M-Sugra models seem to be still very far from detection, yes, even for CTA. It's a very complicated question, yeah. I think that we should at least following the work, pointing the interesting objects, because there are some effects that we were not aware about them, but at the end they are here, they are there. For example, there are some corrections, second order corrections to the gamma reflex that you expect, no? This is regarding the particle physics side, okay? That were rejected in the past because people thought that they were not really important. But at the end, it seems that they can boost some of the dark matter models by 3, 4, 5 orders of magnitude. But what happens here? This is somewhat tricky, no? Because this effect just only affects the dark matter models with the smallest cross sections. No? So if you boost this, or even less, there are models here. No? You boost these ones up to this portion here. Okay, still you are far. But the important point here is that one effect that was initially rejected from the calculations, no? At the end they turn up very important for some of the matter models. So it can be that we are missing something from particle physics or even from astrophysics that can boost the signal importantly, no? So in any case, I think we should keep observing the most promising objects in order to put at least upper limits, so who knows, a positive detection.
You also said that there are some people that are boosting that flux right now, so to higher levels, like close to these lines. Mm-hmm. So what's the motivation for that? Is that just that we can observe it, or there is a physical motivation?
Yeah. As I just told, for example, this effect, which is called internal Verstralum from particle physics, is a second order radiative correction to the annihilation flux that you expect from these interactions, neutrino annihilations, and they can boost the signal. This is very well motivated in principle. This internal Verstralum effect that boosts the signal several orders of magnitude. But for the less preferred, for the models that give you the less fluxes, there are other boost factors, but I think they are more exotic, let's say. Yeah. So this is the internal Verstralum. This is the internal Verstralum effect. Here you have the typical spectrum that you expect from the matter annihilations, and here the effect of this internal Verstralum correction. So it can boost the what you expect from the spectrum, this matter annihilation spectrum. It can boost the signal a few orders of magnitude, indeed, near the dark matter mass. And there is another effect, for example, the Sommerfeld effect, which is, in my opinion, we need to work more about this in a diplomatic way, that can boost the signal also by some orders of magnitude. But in any case, it seems hard to boost the signal in a natural way, at least. Yeah, this is important also. I didn't talk about this. This is a boost that indeed is present. We know it's present. We are trying to quantify how important it is for the matter annihilations, which is the fact of, that we expect in a cold matter scenario that there is a lot of superstructure inside the largest structures. For example, you are looking at a galaxy cluster, You have a smooth dark matter density profile for the galaxy cluster, but you expect a lot of substructure inside this galaxy cluster, like clumps, no, of dark matter, clumps of dark matter particles. Okay, so this can boost at the end. This will boost up the signal also, and we are trying to quantify now how important it is. No? Simulations, for example, are really important for this. For dwarf galaxies, you don't expect the substructure to be really important because they are less massive, no? And you don't expect a substantial amount of substructure there. But for example, for galaxy clusters, they can play a prominent role, a very important role. In any case, simulations tell us right now that superstructure cannot be larger than 200, 300, even for the largest structures right now. So you are still quite far from these 4 orders of magnitude. Maybe 2 orders of magnitude, but difficult. Yeah.
Are there other candidates than gamma rays to detect dark matter? You can maybe in the future combine all because it's true that gamma rays are produced with a lot of phenomena.
Yeah, there is,
even radioactivity and so on.
Yeah, there is a very.
There are other indirect observations you can do. Maybe in the future.
Perfect. Yes. I'm working on that. There is a very nice candidate which is the axion that gives you also very, very, very funny features in the spectrum of AGNs. So axions couple with photons, these gamma ray photons that come from distant AGNs, and they give you a different spectrum at Earth. No? The features are small, of course, but it depends on the energy resolution that you have. No? For example, from Fermi, we expect a very good energy resolution. Yes, and combining all this information, maybe the axion is there, and we can say something about that with a completely different technique, no, than this. No annihilations, whatever. It's just looking at the spectrum of very known principle distant AGNs, and look for these features, nice features that the axion-like particle introduce in your spectrum. Yeah, but it's challenging, of course. It's also challenging, but it's another technique. Yeah. The point of actions, for example, is that they cannot account for the total matter content of the universe. So you have, as you see, you have different problems, different matter candidates.
So, okay, I think we're missing one part of the simulations and also some problems that come from the simulation with the dark matter and also some other problems with this standard model. So tomorrow we will have Martin telling us about some of these problems as well. And also he will speak a little bit about these non-standard cosmological models. Okay. And also maybe on Friday, together with Ricardo, Miguel can tell us a little bit more about the simulations.
Okay. We can just put the slides maybe on Friday and just discuss about the topics that you feel interested in. That's it. No, maybe not give the talk, just